Okay, today in lecture we covered three basic topics related to the fluid kinematics. Fluid kinematics, again, is descriptions of fluid motion. The first tools that we used to describe fluid motion were the lines, the streamlines, sorry for that writing, the path lines, and then the streak lines. I'd refer you to the more complete discussion in lecture today, but in short, streamlines are basically a snapshot of the flow that is everywhere, lines that are everywhere tangent to the velocity vectors. Now, if we wanted to construct path lines within this, we release a particle into the fluid and follow it. I was supposed to start on that particle. Follow it as a function of time. That defines then the path line for that particular particle. Finally, the streak lines are the lines that are formed when we release a dye into, continuously release a dye into a flow. For a steady flow, streak lines will also follow the flow. So here I'm just kind of trying to show a streak of dye that's been released. Now for steady flow, all three of these are equal. So equal for steady flows. In unsteady flows, though, diverge. They diverge, and so not equal when the flow is unsteady. And we did an example of that in lecture today, and I would encourage you to just kind of play around with some other examples related to that. Now, kind of similar to this distinction between path lines and streamlines, we can think about two different reference frames that we might want to use in describing fluid motion. And so we have Eulerian and Lagrangian reference frames. So our reference frames are the Eulerian frame, which is a fixed frame, and then finally the Lagrangian frame, which is moving with particles, moves with the fluid. So that's an F. The Lagrangian frame has certain advantages, especially if the history of particles, positions, and so on matter. It's also very simple to formulate our conservation laws because classical mechanics describe that. But it is the Eulerian frame that we will use for almost all of our descriptions of fluid motion. But we do need to think about how to convert conservation laws that are in the Lagrangian frame into the Eulerian frame, and that's one of the things we'll focus on coming up in a week, specifically the Reynolds transport theorem. Finally, we talked about accelerations. And as we know, accelerations are simply the time derivative of the velocity. But in fluids, since we have both time and spatial variability, we need to apply the chain rule to say that du dt can be split out into a partial derivative with respect to time plus three terms that involve the velocity times the spatial gradient. And in lecture we saw how we arrive at that. But now we can divide these into the local acceleration, which is just the time derivative, and the convective, sorry, I've got my thing hung up here. So convective acceleration are the three spatial gradient terms. Together they constitute the total acceleration. And so when we talk about the accelerations in a fluid, we have to think about all of these terms, or the total time derivative, but it's useful sometimes to divide it into local accelerations, which are actually due to time variability in the flow, and convective accelerations, which are due to spatial variations, but individual parcels of fluid experience that as an acceleration.